So to finish off the problem, it says based on the model you found right there, is there a population limit for the coyotes? Well, if there's a population limit, then that means that as time goes on, what will happen? They'll reach that limit, and then just like the zombie apocalypse problem, they'll just stay there. It'll just maintain that level, all else being equal. So that's like the main thing. As long as the environment stays the way the environment is, it will reach some sort of limiting population. When will that occur? When will that occur? How do we find the limiting population? Plug in infinity. That's when it will occur, is when time has gone on for forever, mathematically speaking. So I plug in infinity right here. What does that do to my problem? It's not e to the infinity, though. E to the negative infinity. What is that? No. It's what? It's a very, very small number. So to see that, I'm actually going to have to write that down, it seems like. So let me go with n equals 650 minus 350 e to the negative 0.4236 times infinity. Well, if I have a negative exponent, then that means that actually that would be a positive exponent in the denominator of that term. So this becomes n equals 650 minus 350 still in the numerator divided by e to the 0.4236 times infinity. Well, infinity times anything is still going to be infinity, right? So this turns into just e to the infinity, which is what? Basically infinity. That denominator is just going to sit there and grow and grow and grow for forever. But if as this denominator becomes bigger and bigger and bigger, what happens to this term? It gets infinitely tiny, until eventually, when the denominator becomes infinitely huge, this basically has turned into what? 0. And therefore I have 650 minus 0, which is 650. So to answer that second question, based on the model you found, is there a population limit for coyotes? The answer would be yes. It's 650 coyotes. That problem was actually a very important problem. The upper limit to a population that you found in the last problem, that 650 coyotes, is called a carrying capacity. A carrying capacity is basically just the maximum population that can be supported by a given environment, given certain conditions that remain constant. So like for those coyotes, there is no hunting season. There is no predator that comes in and starts eating some of the coyotes. There is no disease that's going through and wiping them out. All things being equal, at the time that we took that data, it will have a carrying capacity of 650 coyotes. Okay? So it represents the maximum population that can be supported by an environment given the present circumstances. Models that exhibit this behavior are said to follow the logistic differential equation, which we've already talked about from the last chapter. Now we're actually going to learn how to work with it. So here it is. The rate of change of something with respect to time is proportional to that something times 1 minus that something divided by L. L represents the carrying capacity as time increases. K is your constant of proportionality still. If you solve the logistic differential equation, if you solve this thing for y, or whatever that population is, you wind up with this equation right here. Y equals L divided by 1 plus B, e to the negative kt. B is a constant also. we're going to talk about what each one of these letters does to the function in a second. The important thing is we already know what L represents. So we're going to graph this function, we're going to choose some values for L, B, and K, and then we'll write down what these things actually are based on the graph that we see. So what I've done is I've created the logistic equation right here with just ones in for L, B, and K, and we're going to play with those numbers and see what happens. So the first thing I want to do is screw around with the L on the top. So I'll change that to maybe a 5, and watch what happens to the graph. And now a 10. And one more, 24, and there we are all the way up there. So it is the what? L represents the letter L for limit. The limit on the population as time goes on is the carrying capacity. So you want to write down, where'd I go? There we are. L is carrying capacity for sure. We already knew that. But more importantly, it's the limit on the population as t approaches infinity. Okay, so I'm going to leave, I'll leave L at 24 just so that we can actually see what's going on here. And I'm going to start changing this B value that we have in the denominator. So right now it's 1. I'll make it 2. And watch what happens to the graph. Did it shift? Okay, so we saw something happen somewhere in this region. We don't know exactly what's going on yet. So let me change that to a 3. Still don't know? The y-intercept is changing? Okay. What about everything else? Okay, I'll go with a 5. So it's changing the y-intercept, right? What is the y-intercept? I mean, what is the y-intercept in general? The starting population, if we're talking about a population of stuff, which we are with carrying capacity and logistics growth function, okay? So we are talking about the initial population. This B value is changing the initial population. Is it the initial population? No, it's not. Let me do another one. 11. I'm picking very specific numbers here to clue you into what B actually is. You're right, it is changing the initial population, but it is not the initial population. Let me do one more. This should do it for you. 23. Uh-huh. Yes, that's correct. So what's happening is, as time goes on, obviously we wind up with this horizontal asymptote situation up here. But when time is 0, then this exponent becomes what? 0, which means e to the 0 becomes 1, and I'm left with 24 divided by 1 plus whatever that number is. 24 divided by 1 plus whatever that number is gives me my y-intercept. So, like if I wanted to have a y-intercept at 12, I would change this number back to what? 1. And there it is at 12. Because that e to the stuff turns into 1, and then I wind up with 1 plus 1, which is 2, and then 24 divided by 2, which is 12. So, what I want to write down here is not that B is my y-intercept, but that B does what? I heard something that sounded good. Affects. The initial population. Effects is an adjective. No, an adverb? A noun. Whatever it is, it's definitely not a verb. Affects is the verb. This is a verb. So we need affects. But it is not the initial amount. So affects the initial population, but is not the initial population. Actually, the initial population I guess I could call that y sub 0, y naught, is L divided by 1 plus B. All right, so let's take a look at K. I'm going to leave the carrying capacity at 24, and I'm going to leave our y-intercept at 12. So those two things will stay constant. Now as I adjust K, let's see what happens. As I adjust K, should I see the limiting population change? No. Should I see the y-intercept change? No. So we'll see what K does. Actually, do you have any guesses right now? So it'll be more like a, what kind of transformation? It'd be like a dilation. Yeah. So let's make it a 2. Made it steep. And maybe I can make it a 5, just to really drive this one home. Makes it super steep. If I change it to maybe 0.5, so now I'm going the other direction, makes that steepness shallow out some. So to the point where if I make it maybe 1/8, it starts to get really shallow. So that K value controls how quickly whatever population it is that you're talking about gets to that limiting population. So in our problem, when we had the coyotes that K value was like 0.4 or something like that, that 0.4 would be steeper than that 0.125. But altogether, not all that steep. Okay? So that's how you control L, B, and K. Let's see, what can we write down for K? I like it. K is how quickly a population reaches its limit. So K affects the steepness of the curve. I'll put that on there too. It is affects, not effects. Okay, State Game Commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. What have I just given you? Two given values, 2 ordered pairs. The commission believes that the environment can support no more than 4,000 elk. What does that tell you? A limit. It gives you a carrying capacity, which automatically tells you that you are using a logistics growth equation. Okay? As soon as you're given a limit to the population, you're going to be looking at a problem that looks like this. The derivative of the population with respect to time, the rate of change of the population over time, is equal to proportionality constant times the population times 1 minus that population divided by 4,000. The growth rate of the elk population P after T years. There you go. A couple of mistakes here. That should just be a positive. That should be a positive. I think. Pretty sure it's supposed to be a positive population. All right, so we have a bunch of objectives on this problem. Write a model for the elk population in terms of T. That's just what we've been doing. Part B, graph the slope field for the differential equation. So we'll do that, and we'll sketch it out by hand as well. Use the model to estimate the elk population after 15 years. Once we have the model, that should be a pretty easy task to complete. And then find the limit of the model as T approaches infinity. Again, that should be kind of an easy task to complete. Okay? So the difficulty on this problem is right here. By the way, this is a pretty classic style for a free response problem. I'm not saying that this is a free response problem. I'm saying that it's a pretty typical looking thing where you have like 4 things that you have to do on that same problem. So the first thing we want to do is write the model. Well, I'm not going to sit here and integrate that thing. First of all, because I can't. It involves partial derivatives, and you haven't done any of that yet. That's not done in this class. So we actually cannot integrate that. But we do have a model that was given to us. It was y equals L over 1 plus, right. Instead of y, I'm going to write p, just so I don't get confused. We're talking about a population here, after all. So p equals what? L is what? 4,000. They told us that, so we can go ahead and substitute it in. It's 1 plus, we don't know that b, so we're just going to write b. E to the negative kt. That's where we're at. And yes, we can and we will have to find the b and the k. So we're going to find those by using what? The conditions that were given to you in the beginning. Which one of these 2 conditions is the best one to pick first? Because when we started, we had 40 elk. So I can substitute in 0 for t and 40 for p. So I have 40 equals 4,000 divided by 1 plus b e to the 0, which is 1. So now what I have is 40 equals 4,000 over 1 plus b. So we got to solve for b. What do we do? Multiply both sides by 1 plus b, then divide by 40, and then subtract 1. What do we get? 99, that's right. So b equals 99. Okay, now we need to find k. So we have p equals 4,000 divided by 1 plus 99 e to the negative kt. Other ordered pair was what? 5 years and 104. So that's going to be 104 equals 4,000 divided by 1 plus 99 e to the negative 5k. A little tougher to solve this time, but let's go ahead and solve that. Give me an approximation for k to 3 or 4 decimal places. K is approximately 0.1944 if you need 4 decimal places, 194 if you need 3 decimal places. So we'll go with that. And I just realized something. That's not good enough. Go with that. Okay, so hopefully that's still on the screen. Now, we know K, we know B, which means we can write the equation that part A is looking for, the model for the elk population in terms of T. The model is going to be P, or you could write P of T using function notation, is equal to 4,000 divided by 1 plus 99 e to the negative 0.1944 t. That's the answer to part A. Part B, graph the slope field for the differential equation and the solution that passes through the given initial condition. Now, we're going to do that on a calculator, but we're also going to have to reproduce that on this page, just as a sketch. Shouldn't be too much of a challenge to do that. You're basically just kind of visually copying over from the computer or the calculator to your page. So on our calculators, let's go ahead and enter in this problem as a slope field. So this is what you should enter in for your slope field. Oh, it disappeared. This is what you should enter in on your slope field. You need a differential equation, and remember that the calculator is going to deal with things in terms of y1. P is going to be y here. So when I type in P, I have to type in y. And since this is my first differential equation, it's actually going to be y1. So I found my K value, it was 0.1944, times y1, K times P, times 1 minus, so times 1 minus y1 divided by 4,000. That gives me my slope field. So now that I've graphed that, obviously I'm not seeing the things that I want to see, so I'm going to have to change my window settings. The limiting population for the elk is 4,000, so I need to go all the way up to 4,000 on my y-axis for sure. So menu and window settings. I don't need negative time. I am going to have to change my x maximum. I don't need negative elk, and I need to see at least 4,000 on my graph. So I'm going to make that actually either 4,500 or 5,000. I'll actually make it 5,000. Now for x max, we know that in 5 years we're going to be at 104 elk. We know that we can get all the way up to 4,000 elk, so probably I should go way beyond 10 years from now. So maybe I'll make it 100 years from now and see what I get. So now I hit OK. And that didn't do it for me. Okay, so here's your slope field. And notice that we do have, it seems this is 5,000 up here. It looks like probably around 4,000. It seems like we're kind of going to be leveling off. So this thing is going to take off and then level off as we go. So let's put that initial initial population in here. It says graph the slope field for the differential equation that passes through the given initial condition. So we want to enter in the initial condition that they gave us, which was 40 elk when time is 0. So I can enter that in. So to do that, I want to go back to here, and I'm going to press this guy to bring up my initial conditions. So I can put in 0 time and 40 elk, hit OK, and it should give me a nice looking logistics growth curve. There you go, okay? So now we want to copy this over onto our page. We're just going to sketch that on. So I'll let you guys go ahead and do that. And then we'll go on to part C. So here's part A, part B. We have a slope field going on, and I'm just going to try to copy over these slopes as we go. So I'm kind of shallow here. And then I'm steeper. And then I'm steeper yet. And then I start to shallow back out. And now I'm really shallow. And then on the other side, these things are also coming in from the top. So the interesting thing about this is, if I were to have put a population of elk in here that was beyond the limiting capacity, even above that, those elk would die off because the environment cannot sustain them until that population winds up back here. So you cannot diverge from this limiting capacity. Well, the population, given no other outside circumstances like human interaction or anything like that, the population will always tend back to that limiting capacity no matter what. So now we just draw in our initial situation here. I know my curve is going to look something like this, and I can also put those key values on here. We have 40 elk to begin with. This is my limiting capacity of 4,000, not 40,000. And that would probably be pretty good. The other thing we could figure out is when time is equal to 5 years, we had a population of about 104. So I could put that ordered pair on there, 5 years, 104. And then I should probably also label my axes. This would be time in years, and this would be population of elk. So it's not too hard to draw in a slope field sketch, just as a sketch. You're basically just copying it over from the calculator as you see it. So part C asked me to do what? Estimate the elk population in 15 years. So that's going to be a piece of cake. We have P equals 4,000 divided by 1 plus 99 e to the negative 0.1944, and it's 15 years, so we plug in 15 for t. That's as simple as entering it straight into your calculator and coming up with an answer. What is our elk population after 15 years? $620 exactly? 0.538. So what we're going to do is we're going to say, since we can't have a fraction of an elk, we're going to say approximately 629 elk. Part D. And notice that you should be using not our rounded answer here. You should be using the original K that we found. You can go back in your calculator and use that as an entry here. Okay, so please do that, not the rounded version. You could be off by a couple elk if you did that, and then you'd be wrong if this was an AP free response exam. Okay, part D was find the limit of the model as time goes to infinity. So I want to actually do that analysis. I think we probably know the answer already, but let's write down the equation. P equals 4,000 divided by 1 plus 99 e to the negative infinity, basically. So that would be plus 99 over e to the positive infinity, which makes this what? It goes to 0, because this number, because it becomes infinitely huge again, and then we have something small divided by something infinitely huge, which is essentially 0. Therefore, that's 1 plus 0, which is just 1, and then 4,000 divided by 1, which is just 4,000. And that would be 4,000 elk. So that's it for the problem. And that's it for the section. And that's it for the chapter.